All right, chapter 8 is a study of equations of lines and planes in two space and three space. So we're going to develop some principles building on chapter 6 and chapter 7 from our knowledge and understanding of vectors. Uh, mostly in this case, algebraic vectors. There'll be a component xy vectors in two space, and then in three space, when we move to three space, the xyz component. Lines are represented much like you've seen before with slope-intercept form, but they're represented in vectors in this case, and it's all going to be based on vectors and how line points and lines and planes are represented in both of these spaces. This for students, this isn't really a difficult chapter. The mathematics is pretty easy, and the concepts are just a little bit new, but I think students mostly should be okay with this. Okay, learning goals and success criteria. I won't read these. I'll just leave them here for a minute and make sure that we have these. Okay, and we'll move on to vector and parametric, two things called vector and parametric equations of lines in two space. And this is on page 427. So when we talk about two space, we're talking about the Cartesian, like we're always used to. Okay, so this xy plane here. You guys for a long time now have graphed in the Cartesian two-space plane, right? With x and y. We're just going to redefine how we graph using vectors a little differently here. But again, this builds off of things we've already been doing, and certainly it's not mathematically it's not a big deal. So we've got an example here. Line passing through the point 4, 3. So I'm just going to plot the point 4, 3. 1, 2, 3, 4, 2, 3. That's about here. I'm going to call this P 4, 3. So this is not new, and it follows this line. Okay, this line starts at point P. So that's kind of like our intercept, I guess, in many ways. It's a stationary point that starts to define the line. Much like in the past when we always started with a line with plotting a point. Okay, so look at that as our point, initial point, let's say. Now the line then follows along a direction represented by the vector d, -7, 1. So to establish my next point, I start at my given point and I go backwards 7. Okay, so it's -7, 1, 2, 3, 4, 5, 6, 7, and then I go up 1 unit. And I put a point here, and I'm going to try and draw this. I'm not going to. Okay. Oh, that was awful. Let me undo and try this again here. Wish I could have a ruler. Better. And I'm going to put a point here. Now, officially, some students often do that. Okay, so here I'm just going to establish. Oh, I shouldn't have done that either. Let's undo that. Let's just get that point in here so it's right on that point, and I could call this D -7 and 1. Now we talked about drawing a vector. A vector in a Cartesian plane. So I need an initial point and I need a direction, and that really is how it goes. Now this can continue, and I think I'm going to let this slide if we also continue this, and make sure you please use a ruler. I know it's difficult, my diagrams are certainly not straight vectors here, but that's how you kind of sketch the line here. Okay, now whether or not you include this piece here is really, I mean, if officially it's a line, right? It's 2 points, defined by 2 points, and I'm not going to hold you too much to that, but understand that okay, if I draw it, okay, it's a little different from the Cartesian line. All right, so what have we got here? Okay, sketch the line. We got it sketched. I'm just going to zoom ahead and see if I can talk about equation, how we represent this equation. So our vector equation of a line, okay, is defined by a point and a direction vector, and then this element t called a parameter. Okay, so I'm going to write the vector equation here in a second with that original line that I just did, but I'm also going to write the parametric equation. So we've got two types of equations to represent our lines with vector expressions when we talk about lines into space here. First is a vector equation, so we represent it as a vector, and then a parametric equation that we're just going to expand. So vector equations, okay, let's go back to my original example here. Okay, so a vector equation for this line, okay, is written as r, and then I start with my point, I introduce a parameter, and I put in my direction vector, and on my parameter I'm going to have a restriction where t, okay, can be the element of the real number system. So that allows for the solid black line here. Okay, so that's it. That's it. So this vector equation represents the line that I just drew above, starting at 4, 3, and following along the path, okay, negative 7 and 1. So ideally, this is kind of what we do here. Now, I'm not going to have you do this very often, but if I just set, okay, t equal to 0, t equal to 1, t equal to 2, okay, and so on and so on and so on, and I could even go backwards here. I could go t equal negative 1, t equal negative 2, and as I would do this, okay, just change the values of t following this parameter. What this does is generates, okay, the points that make up the line. So when t equals 0, okay, I don't have anything here. I've got the point 4, 3. Okay, when t equals 1, okay, when t equals 1, okay, I would have, okay, a 1 here. So I have 4 take away 7, that's negative 3. Okay, and then 3 plus 1 is 4. That's actually my new point here. Okay, when t equals 2, I'd replace a 2 in here, so I'd have 4 plus negative 14. 4 plus negative 14 would be negative 10. And then 3 plus 2 is 5. Now, if you notice, that would be the next point over here, so another increment of negative 7 or 1. This is really slow, okay, and if you really pay attention to this, you notice that these points, okay, are going down 7 units in the x component and going up 1 in the y component. The direction vector is slope, and we're going to talk about this, okay, quite a bit starting from this point on here. Just the direction vector, think of it as slope of the line, okay, and this initial point, okay, just think of as, just as I said, an initial point here. We always need a starting point, and then we get our next points, okay, by following along the slope. Okay, and then with vector equations, we get our next point by changing the value of t. Okay, a parametric equation. Okay, so this is a vector equation. Okay, this is a vector equation. So given our point, okay, this is a vector equation. And that's how I defined it here. Now, R actually can be written as components. Okay, so we can write a vector equation like this. So rather than using our vector r, we could just write x, y. Okay, and then if I expanded, x equals 4 minus 7t, and y equals, it would be 3 plus t, right? Hopefully you can see how I got the 7. I just multiplied the t into this direction vector here, so I would have negative 7t in my x component, and I'd have a plus t, or 1t in my y component. Now these are parametric equations. Parametric equations, the way I remember parametric equation is when I expand out my vector equation and I write x in terms of the parameter, t in this case, y in terms of the parameter. Now, parameters, the variable for parameter is not always t, it can be s, it can be any type of equation, that's fine, okay, or any type of variable. Okay, we talked about those. Okay, so let's take the vector equation. Okay, given the vector equation of a line is given by the line r equals 0, 1 plus t, negative 1, 2. So I'm starting at 0 and 1, and I'm going along the direction vector of negative 1, 2. So what's the direction vector of this line? The direction vector of the line, right from my, okay, that's it. That's all I need here, and that should be your direction vector. Okay, find a specific point on this line. Let's find 2 points, actually. Okay, a trivial point and a non-trivial point. Now, a trivial point, by its definition, okay, is when t equals 0. Okay, and when t equals 0, okay, that's 0 here, and that's 0 multiplied by the direction vector, that's negligible. So when t equals 0, our trivial point is just our initial point. A non-trivial point is any other point on the graph. So I can let t equal 5 if I wanted to. Okay, at any arbitrary value. T could be 1, t could be -1, t could be 4. Okay. T can be anything. Now I'm just going to go back to my, get my eraser in this case. I'm going to go back to my original equation and actually find out this point when I set t equal to the arbitrary value of 5 here. So this is going to be 5, okay? So I'm going to have 0.01 plus -5 and 10. I'm just going to multiply the -5 in here. So what's my point? My non-trivial point when I set arbitrarily t equals 5. And again, like I said, it could be t equals 3, it could be t equals 10, it could be t equals anything really, as long as it's non-trivial. So what would my point be when I set t, the parameter, equal to 5? I would have the point 0, -5 is -5, and 1 and 10 is 11. Okay, let's find the points on A and B respectively so that t corresponds to 1. So when t equals 1, what's my point? My point A is going to be 0 take away 1 is -1. Okay, and 1 plus 2 is 3. Okay, and then when t equals 4, that's going to be my point B. Okay, so I'm going to go 0, take away 4. Okay, it's -4. And if I replace this 4 in here, that's going to be at +8. Okay, so 4 times 2 is +8. So my y component is going to be 1 plus 8 is 9. Okay, so explain what the following equation represents. Okay, so the only thing I've done here, okay, is I've rewritten my parameter here. I've set my parameter to be a specific interval 1 to 4. So this particular, okay, when I use my vector equation for a preset, rather than t is an element of all the real numbers, so it's a solid dark straight line, if I set my parameter, okay, to specific values t equals 1 and 4, this vector equation, okay, is set, okay, between, okay, the points. Okay, this would be A, -1 and 3, and this would be B, -4 and 9. Okay, and the corresponding values would be t equals 4 and t equals 1 here. Okay, so that explains what the following means. That's just a line segment, okay, between A, what do I say, was -1 and 3, and B, -4 and 9. Okay, and then finally verify to see if the points -2 and 5, and 2 and 3, the n, 2 and 3 are on the line. Okay, so sometimes points are either on the line or sometimes they're not. So let's verify m. Verify m, -2 and 5. So all I do here is just put in the point -2 and 5, and -2 and 5 into my equation, 0 and 1, and t, -1 and 2. I think that's it. I'm just going to check and see. That's my line. Yep. Okay, so now I expand. Okay, I expand. Okay, I can check -2 equals 0 minus t, and I can check 5 equals 1 plus 2t. So I solve for t for both of them, and they should balance. And if they balance, if they're both the same t, then I can confirm that the point m is on the line here. So for this component, I've got t equals 2. Okay, and it looks like I've also got t equals 2 here. Okay, so since they're the same, okay, I can write that that's a consistent solution is the word here. Okay, therefore, m, -2 and 5 is, okay, or I should say does, let's say does lie on my vector equation. Okay, now let's verify x, verify n here, that's 2, 3. I do it the same way. Plug in 2, 3 into a system where I set it equal to the vector equation. And then I expand 2 equals 0 minus t, and 3 equals 1 plus 2t. So in this case, I've got 2 equals negative t, or t equals negative 2, and in this one, I've got t equals 1. Okay, this is an inconsistent solution, and when I have an inconsistent solution, I can make a statement that, okay, the point does not lie on the vector R. Okay, I gotta pause for a second and move on to the next slide here, and I'm gonna let you guys take a look at this, okay, and see if we can, okay, get this done here. Okay, next up, convert the vector equation into parametric equation. Well, my given vector equation can be written by way of a component. I guess I haven't done this yet. Okay, I don't have to always do this because you're going to get pretty good at this. But I could expand the t in here. That's still xy. And a parametric equation is just when I take the x components. That would be 1 minus 2t, and y equals negative 3 plus 5t. Okay, and that's my parametric equation. Okay, example, find the vector and parametric equations of a line that passes through point A and B. Okay, so first up I need a direction vector, and that's going to be my vector AB. Okay, so that's going to be point B, take away point A. Therefore my direction vector is just a subtraction. Negative 1 take away 2 is negative 3. And 2 take away negative 3 would be 5. So my vector, if I follow along these paths from A to B, I'm following along the path negative 3 to 5, right? I start at 2 and I go to negative 1, so I'm going backwards 3 units. And I start at negative 3 and I go to 2, that's going forward 5 units. So my vector equation is actually really easy to write. If we have this direction vector, I can just write, now I need a point, okay? I can use any point I want. I generally use the first point given, but I can use any point. I could use B if I wanted to. Then I write my parameter, and I write my direction vector. And I want to include this as a sort of a domain. Now my parametric equation is easily written once I have my vector equation. I just expand x equals 2 minus 3t, and y equals negative 3 plus 5t. And again, that was, if you haven't picked this up yet, I know I'm doing this fast, my y component is here and here. Okay, so that's negative 3 plus 5t. Okay, now I still need this when I write my parametric equation as well too. Alright, parallel lines and perpendicular lines. Parallel lines are parallel if they're going in the same direction, right? Now, they might be a scalar multiple of one another, this k factor, okay, but as long as they're going in this, the vectors are going in the same direction. Lines are perpendicular if the dot product is 0. We talked about this in our last chapter. And we also could look at the direction vectors, okay, and perpendicular vectors have this concept where the direction vectors are negative reciprocals. And you guys heard this before when we graph straight lines, negative reciprocals. So if I have a direction vector, I flip it and make it negative, okay? So I basically can just flip that around. I think that should be, yeah, no, here's my original vector, and I can, okay, flip it and make one negative, okay, or flip it and make one negative. As long as I make, okay, one or the other, that's fine. Because if I have a point, or if I have a line, I can have a perpendicular off of each side of that line. Okay, that's the reason why. Okay, so show that L1 is perpendicular to L2. Well, in L1, my direction vector okay, is 2 and negative 1. And in L2, my direction vector is not so easy to find here, okay? L2 is given as x equals 0 minus 2s, okay, and y equals 5 minus 4s. So my direction vector for L2 are these components right here, negative 2 and 4. Okay, so there's my two direction vectors. Okay, so I've got this one and this one. Now I could take the dot product, and if it was 0, I know they're perpendicular. So let's do that by its definition. I don't think we've done dot products in a little while here. So that's 2 times negative 2 plus negative 1 times 4. Okay, I have negative 4. Okay, and okay, so negative 4 plus negative 4. Okay, and that's not 0. Okay, so they're not perpendicular. Okay, so clearly that's not the case here, and it doesn't look like I could even write this combination. Like, I don't think I could write k it's close, but it's not quite. I only have, if I flip this and make it negative, okay, that's not going to be the case here. So I don't have that, okay, that combination of things here. So these are clearly not parallel. Notice that, okay, and I have negative k equals 4. Okay, and that's not going to be, clearly that's inconsistent. Okay? So they're not parallel here. Okay, let's consider a vector, or sorry, a line that's defined by, okay, the vector equation r equals 0 and 2 plus t 2, negative 3. I should have included. Okay, so find the vector equation of a line L2. We're going to call it perpendicular to L1 that passes through a given point here. Okay, so let's take a look at L1. Okay, and specifically this direction vector on L1. Now our direction vector of L1 is the vector 2, negative 3. Okay, the direction vector for L2 is perpendicular. So what I do here, okay, is, okay, I take a look at the direction vector for L1, and I flip the components, and I make one of them negative. And I'm going to make the component that's already negative, I'm going to make that negative. So that's really a negative situation, right? Which makes it positive, okay? So I've got, okay, I just flip it and get rid of the negative, make it a positive here. So I got to do two things. And that's a negative reciprocal idea, right? The reciprocal is a 1 over, but if they're in components, I flip the components, right? And again, you guys have seen this back in grade 9 and grade 10 when you were graphing perpendicular lines. You looked at the slope and you noticed that the slope, there was a negative reciprocal. That's exactly what we're doing here. So our L2 then equation can be written. We have everything that we need. We have our point, negative 3, 0, and we have our direction vector. And I'm just going to write the parameter. Okay, that's it. That's as easy as it gets. Okay, now let's consider, okay, let's look at it by graphing, okay, and see exactly what we've got here. Now I've already done the equations, right? 0, 2, 2 and negative 3, and I'm going to graph L2. Sorry, I'm going to graph L2 to be the point negative 3, 0 plus t, and my direction vector was 3 and 2. And I'm going to graph this one in red. guess I should have written that in red. Okay, but I'll graph this first one in black here. Okay, so just a quick review on how we graph this. Okay, so L1 is going to be 0 and 2, so 0 and 2, and then I'm going to go up to, or sorry, over. Okay, oh, that's not it at all. Okay, I often get when I first introduce this section. Okay, so 0 and 2, 0 and 2 is up here. Okay, and then from here I go over 2 and down 3, 1, 2, 3. Okay, so there's my, that's what I'm going to go. Okay, so back 2, 1, 2, 3, back 2 and down 3, over 2 and 1, 2, 3. Okay, and that line here. Okay, and then in red, okay, I'm going to graph -3 and 0. So -3, 1, 2, 3, and 0 is here. And then I'm going to go up 3, 1, 2, 3, and up 2. Okay, and I'm going to go over 3, up 2, over 3, up 2, and just keep going on and on here. Let me see if I can graph this straight line in red. Whoa, that's thick. I don't want it that thick. Let's undo that. Let's see if we can do it. Move it. Still have it. Good Lord. Okay. I'll give it one more shot here. I need the properties of that line here. I'm going to go to my pen and see if I can do it. Okay, I'm going to see if I can change the properties of that. Select. Yeah, much thinner. Better. All right, there we go. I should have did that in the first place. So there's my, okay, there's my two lines. So this would be L2. Okay, and that's my vector. Okay, and notice that they do kind of look like they're in perpendicular sort of shape here. And this will be L1. That's the vector 0 and 2 plus 2 plus t 2 negative 3. And that's kind of what they look like. Now I could put arrows on the end of them. I should really. I mean, that's how we graph, right? We're good. Okay, so just to recap, equations of lines and planes. Okay, so lines are bidirectional, vectors are unidirectional. So bidirectional lines go in both ways. Okay, vectors by definition go in one direction here, following the direction vector. Lines are infinite in both directions. Okay, and vectors have finite magnitudes, definite location. Okay, and two lines are the same when they have the same direction and location. The lines are coincident. For vectors, okay, vector has no fixed location. It can float. A vector can float. Okay, and two vectors that have the same are the same when they have the same direction and same magnitude. And that's it for this chapter here. And that's a good introduction to lines in two space. Okay, good luck with the homework questions.